So today, let's talk about a force that's literally all around us. It shapes our entire planet, it's inside every atom, and yet you can't see it, you can't touch it. We're diving into magnetism, and it all starts with a very simple puzzle. I mean, think about it. You've probably seen a compass a million times. You hold it, and that little needle just swings around and points north. But why? What invisible hand is pushing and pulling it? That's the mystery we're going to unravel today. Okay, so the first piece of this puzzle is figuring out what a compass needle actually is. It's not just some random piece of metal. It's a tiny little bar magnet that's been balanced so it can spin freely. And the number one rule of magnets is they get pushed around by other magnets. So that tiny magnet in your hand is lining itself up with a much, much, much bigger magnet, our planet. That's right. The Earth itself acts like a colossal bar magnet. It creates this huge, invisible field of influence that little compass needle is just responding to. All right, so we've established there's this invisible force field all around us. But what does it actually look like? You know, if we could put on a special pair of magnetism glasses, what would we see? Well, turns out we can actually make this field visible. Check this out. This is what happens when you sprinkle tiny bits of iron around a regular bar magnet. They don't just fall randomly, no way. They snap into this incredible, elegant pattern. See how they form these beautiful arches from one end of the magnet to the other? For the very first time, we can actually see the shape of that invisible force. This right here is the magnetic field. And that gives us our official definition. A magnetic field is just that, the space around a magnet where its force can be felt or detected. Those little iron filings are basically acting like millions of tiny compasses, and each one lines up with the force, revealing the whole pattern for us. Now, the iron filings are awesome for seeing the big picture, but they're a little messy. To really understand what's going on, scientists needed a more precise way to map out this invisible territory, line by line, to build a much more detailed picture. And the method they came up with is actually pretty clever and surprisingly simple. You just take a single compass, you put it down, you make a dot where the north and south ends of the needle point. Then you pick up the compass and move it, so the south pole is on the dot you just made for the north pole, and you just keep doing that. It's like a game of connect the dots, where the dots are being guided by this invisible force. And when you finally connect all those little pencil marks, what you get is this. These beautiful, smooth, continuous curves. We call these magnetic field lines. Think of them as a perfect map of the magnetic field, showing you the exact direction of the force at any single point. Okay, so now that we've seen the field and we've mapped it, we can start to figure out some of the basic rules that these lines always follow. And these properties are absolutely key to understanding how magnetism works, well, everywhere. So let's break down the rules of the road for these field lines. First, they always flow out of the North Pole and loop around into the South Pole. And they're always closed loops. They even continue inside the magnet. Now, notice how they're all bunched up and crowded together at the poles? That tells us where the force is the strongest. But probably the most important rule, the one that can never, ever be broken, is that two field lines can never cross each other. And that last rule is maybe the most fascinating one. It's not just a suggestion, it's a fundamental law of physics. So why? Why is it completely impossible for two of these lines to ever intersect? The answer is they just can't. It's impossible. And the reason is actually beautifully simple. Remember, a field line shows the direction of the magnetic force. So if two lines crossed, it would mean that at that one single point in space, the magnetic force was pointing in two different directions at the exact same time. A compass placed there would have to point two ways at once, and that's just physically impossible. So far, this whole story has been pretty straightforward, right? Magnets make magnetic fields. Simple. But back in the early 1800s, a scientist named Hans Christian Ørsted stumbled onto something that would change the world forever. He found out that magnets aren't the only things that can create these fields. This right here is his game-changing experiment. All he did was run a simple electric current through a wire, and he noticed that a compass needle sitting nearby moved. It deflected. Then, just to be sure, he reversed the direction of the electric current, and what happened? The needle swung the other way. This was absolute proof that a simple electric current was creating its very own magnetic field. And the conclusion from this was just massive. It meant that electricity and magnetism aren't two separate forces at all. They are two sides of the exact same coin. A moving electric charge creates a magnetic field. Honestly, this one discovery laid the foundation for our entire modern world, for everything from electric motors to the power generators that light up our cities. And all of this leaves us with one final, huge question. We've just seen that electricity can create a magnetic force. So, does it work the other way around? Could you take a regular magnet, move it around, and generate an electric current out of thin air? Well, that's a story for another time.